Among the various concepts of learning differential geometry, there are some concepts which should be learned right at the beginning. Concepts which, if not properly built, would come as a hindrance in your further learning of the subject. In today's video, you would be not only learning those concepts, but also come across some valuable resources which act as a powerful tool in your journey. You will also get a complete view of this subject, which is as vast as an ocean, thereby helping you to form a better idea of the journey that lies ahead. Well, the choice is yours, whether you want to build those concepts right now and then move on, or take it as on when it comes. My name is Shaunak and you are watching this video on my channel Physics for Students. Welcome to the third part on our series of videos on how to learn differential geometry. Before we go ahead with the main video, here is a quick recap of the earlier part, although I have given this in the I button and you can check it in a separate playlist on how to learn differential geometry. Well, first what we did is that we started with the concept of curves and surfaces. And as I told you that before going into manifold, learning curves and surfaces are easier. So there's a comparative understanding of the conceptual complexity and various other parameters which proves that learning curves and surfaces are much easier. We also went into learning what is called a parameterization of a particular equation and thereby a curve, and which proves that parameterization provides an easy way of finding or equating with more than one variables and making things easy. We also looked into some of the fundamental concepts like the tangent lines and tangent planes, what they are, and we also looked into the mathematical interpretation of how these tangent lines and tangent planes actually behave. Taking ahead with tangent line, what we understood is that these are nothing but linear approximation which are used in terms of understanding things better. And why do we need linear approximation? Because tangent planes actually helps in simplified analysis, understanding geometry, and it has got various applications. Now, emphasizing on these facts, we also came across certain books which would help you to understand those various concepts, especially the fundamental concept of differential geometry. I have given a detailed review and an analysis of understanding what those books are, which books actually understands or considers topology to be beginning, how you will avoid those books. Everything is covered in detail in the earlier lesson, that is part number 2. Now we actually stopped here, and now as we go ahead with this part of the video, the first step that we need to understand, because differential geometry is a vast, complex and a very highly mathematical subject, we need to learn that what are the steps that we should follow in order to learn differential geometry. Without following these steps, try to understand that going ahead with differential geometry, getting confused with these concepts of manifolds, curvatures and various theorems leads to frustration, and thereby you think this is not the subject. The first thing is that what are the steps to learn differential geometry? So first we will look into the foundational concepts. Number 1, I'm not going to explain those concepts because this is more on how to part, and then I will tell you what are the books and what are the best books in order to select. Now, first thing which comes across are the curves and surfaces, which I have already covered in part 2, which you can look into it. The next thing which comes is a manifold. Now, spaces that locally resemble Euclidean space but can have a complex global structure are called manifolds. Then you need to learn what are tangent spaces, which are actually vector spaces or vector spaces approximating the manifold at a point. And these are used to define derivative and directional derivative. Next comes what are called vector and tensor fields, functions assigning vectors or tensors to each point on a manifold. And this describes the quantities like velocity, force and curvature. The fifth point is called differential forms. Now these are actually generalization of different functions for integration on manifold. After that comes the Frenet-Serret formula. Now these formulas describe the kinematic properties of a curve in a three-dimensional Euclidean space. What I'm trying to mean is that they involve curves tangent, normal, binomial vectors as well as the curvature and torsion. Then comes what is a broad area which is called tensor analysis, and this is a foundation very much to differential geometry, and it provides a language for describing geometric objects and their transformation. And then finally comes what is called the exterior calculus. This provides a powerful tool for integration on manifolds and studying the geometric objects. Now, why I told you all these points is that maybe there are certain other areas like Gauss-Bonnet theorem, etc. But these concepts will provide a foundational understanding. And if you are not understanding or grasping these 8 concepts, then exploring the further areas will become very difficult. So take up a lesson, try to understand, get your notes done that these are the first initial concepts in differential geometry that you need to learn. Without that, moving ahead would be an act of foolishness. So these are the fundamental concepts, and this is part 1, which is called foundational concept. The next concept that we have is what is called a metric geometry. Now, why do I mean by that is that metric geometry is very important. So what do we mean by metric geometry? It provides the qualitative tools to study the different shapes and properties of manifolds. So metric geometry is a fundamental branch of differential geometry which focuses on the concept of distances and measurement, because it's called metric. So you need to measure something. So metric geometry, there are certain concepts in that. So number 1 is what is called the metric sensor. As you know, it is a symmetric positive definite sensor that is an inner product on each tangent space in a manifold. It is, you can say, an essential way to measure distances of the angles locally. Then comes another subject or concept, I would say, Riemannian geometry. Now, this is the study of manifolds equipped with what is called a Riemannian metric. It is a cornerstone of differential geometry, and it extends the geometry to surfaces. The third thing which comes up are geodesics, which you already know are the shortest paths between 2 points on a manifold determined by the metric. And then, as I was talking, is called the Gauss-Bonnet theorem, and this acts as a bridge, between the Gaussian curvature and the Euler characteristics of the surface. So part 2, after going through the essential lessons of the foundation, you need to go for metric geometry, because metric means measurement. So all metric tensor, Riemannian geometry, geodesics, Gauss-Bonnet theorem are basically doing what? They are tools to measure the distance and the angles and whatsoever. The next step into understanding differential geometry is what is called the connection and curvature. Now, connections are of different types. Let me tell you that what do we mean by connection? It is not the typical type of a Euclidean connection, but it actually compare vectors at different points of manifold. It is just like having a tool or a car or a vehicle in which you can transport a vector from one place to another, keeping its direction as consistent as possible, because it should be invariant. Now, connections can be many. Affine connection, covariant derivative, torsion tensor, and so on. I'm not going to mention those because those would be subject driven, but try to understand that you need to understand connection and curvature. And as I told you, then you need to understand what is a curvature. I mean to say there are many things which comes under it. It is basically how much a manifold deviates from a flat or a Euclidean Cartesian space. That is what is called a curvature. So this covers the second part, which is called connection and curvature. Now, there are many topics, although the list would be very exhaustive and long. I have just shortened it in a few lines, that there are certain additional topics, or which we can call extra. And there are a lot of researches nowadays going on these extra topics. I will just cover up what do I mean by that. The first one are called Lie groups and Lie algebra. And these are understanding of the symmetry and geometry of transformation. Then there's a very important concept which is called a fiber bundle, and these are basically generalization of vector bundles in gauge theory of physics. Then comes characteristic classes, which are basically invariants with vector bundles, and there are a lot of index theorems also. Apart from this, we have something which is a very complex subject, which is called a symplectic geometry. Then we have complex and Kähler geometry, or we can say Kähler manifold, and there is a global differential geometry which actually studies the properties of independent local coordinates like topological invariants. Now, it is not a very exhaustive list. It carries many other important topics. A lot of researches are going on. But these are just few examples, just to give you that you can carry on and explore further topics and understand what actually it is in terms of more abstract mathematics. Now, these are the steps 1, 2, and 3. So overall, these are the topics that you need to understand. Now, the next point is that you might have a question that why do we need to learn those steps? What is the reason? Is it that we just divided for the sake of making this video? No. The first thing is that it provides a very clear learning path. That means it actually clears the path for learner to progress from basic to complex concept, and it outlines which concepts serve as a foundation. As I told you, otherwise you get into differential geometry without understanding anything. The second thing is that it allows you to concentrate on specific areas, because now you know what are the areas that you know and what are a little bit weak, you need to concentrate more. And time management, it also helps in allocating study time effectively. It also helps you separating this concept into levels can enhance your understanding of the relationships, and it also gives you a holistic view in order to get a big picture. And also it provides something which is called an effective teaching, because if you're a teacher, you can tailor your curriculum, instruction, you can design courses based on different levels and provide the clear guidance for students in the course of progression. So what we can say is that if you divide the understanding of differential geometry, then it becomes easier to navigate, to learn, and you all already know that these are the areas which you need to concentrate more. Now, having said all the Frenet-Serret theorem, the Gauss-Bonnet theorem, etc., you might have a question that what are the books? What are the books of to learn? So in this part of the video, I will just cover up two important books. As I always say that you should not go for what is called a choice overload. That is devastating. That is very detrimental in your course of learning. So have few books and try to go through that. Now the first book, which is a little bit mathematical, I will come across two books. The first is the very famous Sir Lang's book on graduate text in mathematics, Fundamentals of Differential Geometry. The Amazon rating shows under 60 star, but it is okay. I understand maybe people have not understood the mathematics, so they've given a 4 star or a 3 star. So I can tell you that among the many books of the fundamentals of differential geometry, this is, I would say, is quite exceptional. The reason is that you know who is Sir Lang, or rather I would say the Sir Lang's way of delivery and making up this book. It is for a wide audience. Let me show you how beautiful this book is and what are the concepts that it covers. It will just match exactly what are the foundational concepts I told you a few minutes earlier. So the first, it will start with what is a differential theory. Then it will cover a differential calculus, manifolds, vector bundles, and then it will cover a vector fields, operations on vector fields, and the theorem of Frobenius. So as I told you, these are the foundational concepts. So this book covers all those. Next, it covers curvature. As I told you that you need to understand curvature, then the curvature and the variation formula, then the automorphism and symmetries, then comes the forms of integration, where you can find the Hodge star on forms, integration, different forms, Stokes theorem, and so on. One important part of this book is that the author has straight away written that the present book aims to give a fairly comprehensive account of the fundamentals of differential manifolds and differential geometry. So you get a very clear understanding that what Sir Lang, Professor Lang is trying to mention. The size of the book influenced where to stop and where would be enough material for a second volume. Right. So at the most basic level, the book gives an introduction to the basic concepts which are used in differential topology, differential geometry, and differential equations, and so on. So you can read. So this is a very clear-cut idea what the professor tells you. So from my opinion, I can tell that this is just the right book you need to know. This book contains just the right mathematics that you need to start learning, and it is a purely mathematical book. Remember that there is no intuitive way of explaining things, etc. Now, having said that, you might be thinking that if you need a book which is a little bit easier than the pure mathematical or the rigor of mathematics, then this is the second book which you can very well go through. This is written by two authors, Joel W. Robin and Dietmar A. Salomon, Introduction to Differential Geometry. And this is a textbook which is suitable for one semester lecture courses. I have given a kind of a review. So the first chapter actually will give you a historical overview which set the context for the learning, and then it will go into manifolds. It covers Levi-Civita connection, geodesics, and other things. So in all, I will say you that this is a fairly a kind of an intuitive book which is not too mathematical as Professor Lang's book, but gives you a very holistic understanding of all the things that you need to know about differential geometry. Before I go ahead and share you with the content, I would like to show you how the book is arranged, and so beautifully the two authors have given an understanding. So first one, it shows you that chapter 1 gives you a brief historical introduction. So these are snapshots from my book, remember. The second one, it shows about, introduces the foundational concepts of differential geometry, defining manifold, extrinsic setting, etc. Then it comes with the third part, which I told you is the connection. You see, this is the way it is arranged. So Levi-Civita connection, covariant derivative, vector fields, etc. So 1, 2, 3, 4, 3 chapters are done. Fourth chapter, obviously it comes with the geodesic part and it defines the length of curves, etc. Then chapter 5 introduces what are called isometries, as I told you, the curvature tensors. So the Riemann curvature tensors, the generalized Gauss's theorem, theorema egregium. Chapter 6 contains some more answers which can be viewed as when are two-fold manifolds isometric, etc. So chapter by chapter, right at the beginning, the two authors makes it very clear. And then the final chapter, chapter 7, it deals with various topics that are at the heart of the subject. So it will actually go back to Morse index theorem, which follows from chapter 4. And then the third section will build on chapter 5. So it will give you a kind of a brush up, a summary, or a little bit more emphasis on these areas which are covered earlier. Here is a quick understanding of the book, the content. So you can see how it starts. So it starts with coordinates and then moves into the foundations, tangent space, derivative, etc. Then it will come into the connection, the Levi-Civita connection, the parallel transport, covariant derivative, then the motions and developments. I told you that you need to understand the physics part also. So the motion, sliding, twisting, wobbling, etc. Then the Riemann metrics, and then comes the geodesics. Apart from that, it will also cover Riemann curvature tensor. So the curvature part is covered, including theorem egregium, geometry and topology, and then the topics in geometry, the chapter 7, which is the killing vector fields, the Lie groups, the isometry of Lie groups, and so on. So this would be, let me show you what I feel about this book after showing you the content. So it is easy to understand and it carries beautiful colorful illustrations. These books, along with the mathematics, also describe the concepts at length and gives you a clarity. And just like Professor Lang's book, this is also, I would say, just the perfect book. It contains exactly the chapter and the explanations, and it has neither less nor more. So you can say that this is exactly the type that you need to know in order to clear your foundation concepts of differential geometry. Now these two books, which I would say these are good enough to provide you the knowledge, the understanding, the foundation being clear. But one thing which I would like to emphasize now is that this concept, which is called a manifold. Now manifold is another concept which requires a little bit more attention, and in the next part of the video I will show you some very beautiful resources and try to understand this concept, because this is a very important concept without which differential geometry, a learning of differential geometry won't be complete. First of all, we will try to get an intuitive as well as a mathematical understanding of what is a manifold. Now, as you can see, if I take the word manifold, it is divided into two. The many and fold makes up the word manifold. If I go by literary sense from the West Saxon and Middle English, more or less it means many. So mangifield, many, all this means many. And if I go again literary sense with the word fold, it is fald, field, or vowed. So overall, if you can take the meaning is any object which has got many kind of a variation. So here you can see it has got numerous different parts consisting or operating of kind or combined and having many different features and form. And fold means obviously to wrap up or furl or to bend or ply or anything. So this is actually the literary meaning. Now we will go to the mathematical understanding, because all these carries the root in literary sense. So I just thought to give you an understanding. So anything which has got many bend over itself, something which is called a manifold. So we can say these are topological space which deals with numerous shapes and forms that are bent, furled or warped, wrapped, and one part lying over the other. Don't worry about the term topological space. It is not very important and pertinent to today's discussion. So we can say that every point on a manifold has a small area which looks like Euclidean. I will show you what do I mean. And another way of defining is that it is a topological space that resembles locally as an Euclidean space. So both of them means the same. That means there should be a surface which, if zoomed, will be a little bit more Euclidean. Let me show you a schematic diagram. Suppose you're standing here on the globe and you keep on moving from this part to this part and this part to this part. So what you can see that you come at this end and you end over here. Now if I try to zoom this globe, say for example this is a global area, so I'm trying to zoom that. So what happens when I zoom it further and further, it becomes something very flat. And then I can start walking and joining those red dots one by one by one by one. And then I can come to the same point. So overall the movement is the same, but I have zoomed this part and I have made it flat. This is the very concept of manifold which I try to explain, that a part of the globe should locally resemble Euclidean, you can say flat or whatsoever, and the advantage is that once you make it Euclidean you can use the rules of calculus and things becomes very easy to visualize. So this is what is called a manifold. You're focusing, zooming and making it locally Euclidean. So from here what we can say, this part is a global where we are watching it right above the earth, and this is local, so it resembles flatness. So these shapes, and you can see these yellow boxes, what I can do is that I can extrapolate these and we can say that these are all x1, x2 and it goes up to Rn. That means it is up to the real number up to the point n, and these are more or less isomorphic to each other. So from here we get a definition that a manifold is a space, or I should avoid the term topological space. I should say manifold is a space that is locally isomorphic to a Cartesian space. Obviously the box is a Cartesian space and this is just locally isomorphic, because if I take those yellow boxes and if I zoom and I can apply the rules of calculus, so we can get what is called a manifold. Now from here we move to a little bit of a mathematical definition. So what we can say is manifold obviously is something which locally resembles an Euclidean space. So we can say that in a kind of a n-dimensional manifold in a topological space M, if you take a point for example x, which is I would say which would be in M, and then we can say that has a neighborhood which is homeomorphic to the space Rn, obviously. And we can say, so it should be homeomorphic. I'm not showing the animation or the understanding of homeomorphic, but those who understand, it has to be homeomorphic, otherwise it won't be a manifold. And we can say that it is something like we are taking a geometric object from Rk and we're trying to fit in by Rn. Now fit in, by word fit in, I'm trying to say it is embedding. So when we talk about going from Rk, which is a dimensional space, positive integer as you understand, to Rn, we are typically referring to a function or mapping that takes point from a k-dimensional space and we can put it into the n-dimensional space. So in the context of manifolds, we often talk about embedding a manifold, as I told you, into a hard dimensional Euclidean space for visualization or computational purposes. So from here what we can say, that if we take a line, just a straight line, and we try to embed a line or wrap it around a circle, how would it look like? Say for example this is a circle and I take different colors. I take a blue one, I try to wrap over here. I take this one red one, I try to wrap over here. I take this one and try to wrap over here. So what is happening is that each arc is trying to wrap over the circle. And if you take it closely, if you zoom the arc closely, you would see that it is an infinitesimal arc and it will locally resemble what is called a one-dimensional line segment. This is what is the beauty of manifold. So if you zoom and zoom and zoom it, because it is an infinitesimal arc, it will just become a line segment. And each time I'm trying to wrap it over the circle. So this diagram you can see now, which is from the Wikipedia, this actually shows you a better. So the yellow one, the blue one, the green one, and the orange or the red one, all of them have been able to wrap around this circle. So from here what we can deduce, that any closed loop in one dimensional is a manifold. Why? Because you can just imagine in this fashion, which I just told you, that you can imagine wrapping it around into the right shape. Another way of to think is that from a line segment you can find a continuous one-to-one mapping of the loop. So here you can see the circles, the parabola and the cubic curves, all are basically one-dimensional manifolds. So the key property of a manifold is that Yeah, so the closed loops are the easiest one manifold. So the key property of a manifold is that every point of a neighborhood that looks like a piece of a Euclidean space. So if we get open-ended curves that extend out to infinity, which are natural mappings to one-dimensional line. Now this you can understand what is a manifold, but also you cannot just pick up a surface and you tell, okay, this is a manifold. No. For example, let us see this figure 8, which is a sign of infinity. Now what happens is that, as you know, the key properties of a manifold is that every point has a neighborhood that looks like a piece of a Euclidean space. This intersection, which is just pointing out here, the intersection point of the figure 8 curve does not satisfy the condition. Why? Because there is no way to find a neighborhood around this point that resembles a straight line or a piece of a one-dimensional Euclidean space without encountering another part of the curve. So remember, every surface you cannot just tell it is a manifold. I have shown you an example of figure 8. This is typically not a manifold. And the reason is that there is no way to find a neighborhood around this point, which I am just pointing it in a purple arrow, that resembles a straight line. So a very easy example is our Mother Earth. We know that Earth is round, but as soon as we stand on a field, it looks flat. So that means what? That locally it is flat. So we can of course have higher dimension manifolds which can be embedded in large dimension Euclidean spaces, but these are difficult to visualize. Now if you move into what is called a two-dimensional manifold, as you can see, these sphere, torus, double torus, cross surface, Klein bottle, these are all examples of two-dimensional manifold. So as you can visualize from here that the simplest one is a sphere. And you can imagine that each infinitesimal small patch, which is showing it here in small patches, small boxes of the sphere, locally resembles just as a two-dimensional Euclidean plane. Similarly, any two-dimensional surface that does not self-intersect is also what is called a two-dimensional manifold. Now you might have a question that Klein bottle, as you can see, is a kind of a self-intersecting surface. Then how come we can say that Klein bottle is a two-dimensional manifold? Well, I won't say it. If you know why a Klein bottle is, in spite of being a self-intersecting surface, is a manifold, please let me know in the comment box, and I will wait for this comment, and I would like to know from you. So if we go in terms of the mathematical understanding, here you can see n-dimensional topological manifold. M is a topological Hausdorff space. I hope you understand Hausdorff space with a countable base which is locally homeomorphic to Rn. And what does it mean? It means that if you take a point P which is in the manifold M, there is an open neighborhood of U of P, and there is a homeomorphism which is phi U maps to V, and this map U on the open set V is a subset of Rn. Now all these M, N, etc. won't be clear until and unless I give you a pictorial understanding, and this is the picture which I'm going to explain you a little bit into the next part of the video. Now here you can see first of all our manifold, in this case X, this one which I just highlighted, this one, which we can imagine is a manifold in some high dimension, and we can take it as n plus k. Now we have two different patches or domain which is defined by u alpha and u beta. These are two different, I would say, patches, or you can imagine as local coordinates neighborhood defined by u alpha, the green, and the u beta, the purple. Now since purple, which is in X. Now since it is a manifold, we know that each point locally has a mapping to a lower dimensional Euclidean space, say Rn, via this one, phi, which is basically a chart or a coordinate system. Now if we take a point P in our domain, so here it is, since it's a map, it's a manifold, we know that it is locally. So if we take a point P, then we can say we can map this P into a lower dimensional Euclidean space. The mapped point is called the coordinate or local coordinate. And finally, if we have a bunch of charts whose domains exactly spans, then the entire manifold is becoming what is called an atlas, although I have not shown in this part of the video. So this is what is called a manifold, both mathematically, intuitively, and understanding the different types of manifold, etc. We will come to that part later. But first of all, when we have understood manifold, which is a very internal, inherent understanding of the concept of differential geometry, you might have a question that who actually coined the term manifold, or where from the word manifold actually came from. And for that we have to go to our granddaddy of mathematics, none other than who is called Bernhard Riemann. Now, Bernhard Riemann, a 19th century German mathematician, is credited with laying the foundation of modern understanding of manifolds. Now, he actually, I have not covered his life, but anyway, he was a very poor person, and his father went totally bankrupt to send him to the Göttingen University under the savant tutelage of Carl Friedrich Gauss. And his 1854 habilitation lecture at the University of Göttingen, titled On the Hypotheses Which Lie at the Basis of Geometry, is considered one of the most influential works in the entire history of mathematics. This is the Göttingen University. His father went bankrupt. He went to Gauss. Gauss gave him a very difficult topic, but he came up with something which is phenomenal. This is actually the word or the term manifold, right? This is the term manifold, and it actually comes from the German word which I won't dare to pronounce. It would sound so foolish, and it actually means diversity. As I told you, many and fold, it actually means diversity. So is a German word used by Riemann, and it is now called manifold or manifoldness. So in this lecture, Riemann introduced the concept of what is called the n-dimensional manifold, and this is a revolutionary idea, remember, at that time, as it challenged the prevailing Euclidean view of geometry, and Riemann envisioned, as I have written, spaces with curvature and different dimensional properties, laying the groundwork for non-Euclidean geometries and differential geometry. Also, let us remember that this word is the German word used by Riemann for the concept of manifoldness or variety, conveying the idea of space with multiple aspects and dimension. Now, Riemann's intuition was to consider spaces that could be locally described by coordinates, but whose global structures can be very complex. So first is that Riemann's groundbreaking work generalized the concept of space beyond the familiar three dimension. Number two, it introduced the idea of curvature, showing that spaces could be curved. Third was, it laid the foundation of differential geometry, providing the mathematical tool to study these curved surfaces. So Riemann's lecture was a pivotal moment, remember the book we will now see, for the development of mathematics, and his ideas continue to shape our modern understanding of the universe. So what was the idea? The idea was to get something which could be described by local coordinates, but the global structure can be quite complex. So this is the famous book of Bernhard Riemann's thesis, and you can see who has translated. Another legendary person, William Kingdon Clifford, and he actually mentioned this term as manifoldness, or we can say what is called a variety. Now, in his Göttingen lecture, Riemann described the set of all possible values, I would say values of a variable with certain constraints, because the variable can have many values, obviously. He distinguishes between this one, which is called a discontinuous manifoldness, with what is called a continuous manifoldness, depending on whether the value change continuously or not. As continuous examples, Riemann refers not only to colors and the locations of objects in space, but also the possible shapes of spatial figure. Using induction, Riemann constructs this, which in English means n times extended manifoldness, or n times n-dimensional manifoldness, as a dimensional manifoldnesses. Riemann's intuitive notion of this word actually evolved into what is called manifold today, and Riemannian manifolds and Riemannian surfaces are named after Bernhard Riemann. So we see that Riemann himself in his lecture used this word, and which is almost synonymous to what is called a magnitude, saying that he is he set himself the task of constructing the notion of a multiply extended magnitude, and involves different intuition when using this first word. So now you understand that why he used this word, which means magnitude, and magnitudes can be many, variety, a lot, which involves diversity. So that is why the constructing the notion of multiply extended magnitude. So this is after how he died, and he was very ill, and he married Alice Scotch, and then in order to overcome his illness, he died at Sicily on July 1866, just I think around 42 years old. An influential mathematician, and this is how the term manifold came into being. Now, are manifolds only one-dimensional, two-dimensional we have seen? So let us quickly see some of the photographs, or I would say pictorial detour of understanding what are the different types of manifold. So one-dimensional manifold can be a long line, a circle, or a real projective plane, something like this, which is called a real line. Two-dimensional manifold can be a cylinder, a Klein bottle, a Klein quadric, a Mobius strip, and a sphere. Well, three-dimensional manifolds are a little bit difficult to visualize. It can be a three-sphere, a solid torus, or what is called a Whitehead manifold, named after J.H.C. Whitehead, was the founder of the homotopy theory. Now, when we understood the types of manifold, there are two things which need a little bit clearer understanding. That is what is called a smooth or a differentiable manifold. Now, when I put in or, I don't mean to say that which one you should study. You should study both. But what is a smooth and what is a differential manifold? Coming up into the next part of our video. Now, when we talk of smooth manifold and differential manifold, we mean smooth means that not only topologically like Euclidean, but allows for smooth functions. And what do I mean by smooth functions? I will come to that part later. But differential manifold is something which is similar to a smooth manifold, but it has a little bit more flexibility. That means more generalization. That means you can at least take one derivative, maybe more. And smooth functions are those which are infinitely differentiable. That means you can take derivatives of first, second, third, and so on. But differentiable manifold are, means that the curves and functions are differentiable, that might have some kinks or sharp turns. So these kinks and sharp turns are not in smooth manifold. So a smooth manifold we can say as sphere, when the entire structure is very smooth, and this is what is called a differential manifold because it has what is called kinks or sharp turns. Here is a comparative understanding between smooth and differential manifold. This is a special type of a differential manifold where it must be smooth. That means you can infinitely differentiate and so on. But differential manifold only allows for functions that are differentiable. Smooth manifolds actually are more restrictive because they have a higher level of smoothness. Differential manifold obviously are more generic because they can accommodate both smooth and those which are called kinks and sharp turns. These are transition functions which are infinitely differentiable, and in the context of differential manifold, the transition function between overlapping charts must be differential manifold. Now from here we deduce a wonderful line, that is all smooth manifolds are differentiable, obviously. This is the higher structure, but not all differentiable manifolds are smooth. And you can read this one, this is wonderful. Smooth manifolds are very well behaved, but differential manifolds are not well behaved. That means it has got a roughness, and where you can take at least one derivative. And it is about the level of smoothness or differentiability that you can create to have mathematical or physical models. So both of them are important, but this is a kind of a comparative understanding. Now, as we are talking about what is not a manifold, we understand what is a manifold, that has got a neighborhood, etc. But let us see some of the ideas of what is not a manifold. So we understood this, that there exists a neighborhood and should be homeomorphic. But as you can see this one, this cusp, every neighborhood will contain two intersecting lines. Hence, to find a homeomorphism is not possible. Thus, it is not a manifold. This one you have already understood quite clearly, that this at the point they are intersecting, we cannot find in a neighborhood. that resembles a set of a Euclidean space. Also a cone with a vertex. This one is also not a manifold. Why? Because no matter how small a neighborhood you consider, it will always contain the sharp point of the cone. A sphere with a hair. This is also not a manifold because it is a point where a line segment is attached to a sphere. And the famous Cantor set. This is also is not a manifold because it has a fractals. And fractals, remember, they are not smooth. Now, having said that, we come to the most important part, that how can we learn those and what are the books, or what we can say, what are the best recommended books for learning manifold. In here's manifold, I mean to say obvious smooth manifolds. The first book is a very famous one by Loring W. Tews, which I have cited in many of my videos. Introduction to Manifolds, 88% 5-star rating, that is amazing. And this is the famous Taiwanese American mathematician. He attended McGill University and his doctoral advisor was none other than Philip A. Griffith. So this is a nice book, and it starts with chapter 1, Euclidean spaces, then it goes into vector fields and so on. The book also covers the exterior algebra, which I told it is important, multivector, the tensor product, the wedge product, and then differential forms or Rn. So it is not only a smooth manifold book, but a complete understanding of differential geometry. Let us see what are the important chapters which are covered in this book. The first part is that manifolds. It will cover up with a brief introduction of Riemannian manifold. Most importantly, what is a smooth manifold? This is wonderful because smooth manifolds are easier to understand. Smooth manifolds are manifold, smooth maps between manifold, all those things are covered. So first part, then it will cover diffeomorphism, the inverse function theorem, and it contains very beautiful diagrams which make things easy. So first part would be the manifold. As you can see, it starts with topological manifold, smooth map manifold, which is very important. The second part will be the tangent space. As you can see, it covers a very detailed understanding of a tangent space, tangent bundle, categories and functors, followed by the submanifolds. Post that, it will obviously compare what is called Lie groups and Lie algebras and so on. I have not mentioned, otherwise it will take a long time. So my honest opinion about this book of Loring W2 is very well arranged, a very well designed book. It concepts the clears up a lot of concepts in manifold. Language is pretty simple and one of the best book to start learning manifold. But as I always tell, that one book is not good enough because you might find up some problems. The next book is even better. I would say it's great famous by John M. Lee, Introduction to Smooth Manifolds. This is the customer rating, the product details, and this is the famous Professor Lee, born in the University of Washington and graduated from Princeton University. Now this book requires a special attention because in this book there are certain details which the professor lays out before going ahead into that. The first one is that you see it has clearly written it is a book for the first graduate text on manifold theory. And it assumes that you know general topology. This is important. The earlier book doesn't assume that. So, covering spaces. The book is similar in philosophy and scope of the first volume of Spivak's classic. So, here also it is written, I try to keep the approach as concrete as possible with pictures and intuitive descriptions and how one should, discussions, how should one think geometrically, because moving from abstract concept without shying from the powerful tools of the modern mathematics. So, you understand that he is trying to give you the geometric understanding. Why? Because abstract concepts sometimes become very difficult. But remember that you need to have a basic understanding of general topology. So here is a kind of an understanding of the book, a brief content. So it will contain the submersions and immersions, etc. Then it contains the tensor parts. I've just highlighted the major part, the algebra of tensors, etc. Then it contains the differential forms, the geometry, value, measurement, symplectic forms, etc. Now, if you are really willing to know a little bit more on the lectures in the sense that you don't want to go through books, but you just want to go through the online resources, then I will just tell you there are a few beautiful online resources, and among them, I would say, I'm putting up the link in the description. It is one of the University of Notre Dame, and this is called the Lectures on the Geometry of Manifolds. This is by Liviu Nicolescu. I'm sorry for the wrong pronunciation, and it covers a lot of topics. I will just show you manifolds, natural construction and manifolds, Riemannian geometry, and so on. It's a very extensive lecture which you can find. The link is there on my description. The second is obviously the one and only MIT open courseware, Geometry of Manifolds. All these are on PDF. I'm putting up the link on the description box through which you can check in. The third one would be the mathematics lectures on smooth manifolds from the Radboud University. This is also a nice and wonderful book which is fairly old, 2017, but doesn't matter. These things will be the same, which is Manifold Lecture Notes, Fall 2017. And lastly, what I would say is the LSA mathematics. This is also a nice kind of a lecture. You can download manifolds.pdf. This is also a beautiful understanding on the concepts of manifold. I think it is not much of a page as far as I remember that this is beautiful. So from here, can we draw a summary of our understanding? That first you need to understand the division of differential geometry, which is going to give you much more better clarity and help you assess the current knowledge. You can understand the basic concepts of differential geometry and learn the concept of manifold. What is not a manifold is also important. Understand what is a smooth and a differential manifold, and select any book, any online resource, anything that suits you. Because at the end of the day, the entire concept and the objective of this video is that you learn easily, you learn beautifully, and you learn with a lot of fun. So that's all for today's video. Thank you very much for taking up your time and watching this video. If you have liked, please do not forget to hit on the subscribe button and click on the bell icon to get all the notification from my channel Physics for Students. This is my email ID which you can write, and this is my other channel where I post videos on general theory of relativity. If you want, you can follow me on my Facebook, LinkedIn, Instagram and Twitter account. Thank you very much. Physics for Students will be soon back with more videos, but till then, goodbye.